The following content has been provided by RWTH Aachen University.
Okay, everybody, welcome to iOS application development today. This should be a fun class today and tomorrow. I'm really excited to share a completely different way of building iOS apps with you from what you've learned so far. Because we've seen the UIKit way of doing things, which has been long established and is the way that most apps that are out there have been built so far. But we're now going to see sort of the new kid on the block that is an alternative to how you can create applications on iOS, which has a couple really intriguing qualities that I want to share with you. So we're going to take a look at SwiftUI today, and tomorrow we're going to go a little further and see a couple of the more involved topics around SwiftUI. Nothing too advanced because we still have a seminar topic coming up on the really cool stuff with SwiftUI, but we will cover sort of mostly I could say the output side today, sort of looking at how you arrange things, how you create views, and then tomorrow we'll get at the interactivity, how you link your code to your UI so that you can have input from the user, have that input change your data model, etc. Where does SwiftUI coming from? Well, as you may know, Apple at some point replaced Objective-C, right? Objective-C was a programming language from the 80s. It was really great when it was used for Next Step, and then Apple bought Next, and then they turned Next, the Next Step operating system into macOS 10. Basically, Objective-C stayed the programming language for the operating system, and they went really well together. They really worked well. But then when Apple sort of moved from the desktop, macOS, to where AppKit was the user interface toolkit, to mobile and created UIKit, there was still Objective-C, right? So UIKit was also still designed around Objective-C. It was really, pretty much a sibling of what was going on with AppKit on the desktop. So all of these created with Objective-C, and then in 2014, Apple released, after they'd been working at it for like several years, I think 2010 was when they started with it, they released Swift. And Swift was really their step to say, all right, we've been working with one programming language now for pretty much 30 years. It's time we do a major cut because, as you all know, programming languages have advanced, right? We've got more modern concepts that haven't been around in older languages. So Apple, like many others in the business, said it's time to move to a new programming language. So they introduced Swift in 2014. But at that time, UIKit was still the only way to build mobile apps, right, on iOS. And so Swift was, in part, designed by Apple and also the open source community. It's a shared project to be able to work well with UIKit. But that wasn't its sort of core goal. So it wasn't like Objective-C and AppKit had really evolved sort of in close lockstep. They were all really working well together. So Swift was kind of like made so that it would work reasonably well with UIKit. But you can see, and you probably noticed this, that some things seem almost a little alien when you look at how Swift wants you to do things and how UIKit wants you to do things. It wasn't quite the perfect match. And so meanwhile, development of SwiftUI started at Apple just 1 year after the first version of Swift came out. And if you've been following Apple in recent years, you know that the first version of Swift wasn't exactly the version that was meant to stay, right? Swift changed heavily in its first couple years, drove lots of early adopters, yours truly included, kind of mad because things kept changing and you couldn't build code that would still compile with the next version, and there were ABI problems, not just API issues, but application binary interface issues. It wasn't until 2019 that actually Swift settled as a language, settled down enough to say we now have a stable binary interface for the language. And that's pretty long. Meanwhile, SwiftUI development was going on at Apple. And it was inspired by saying, well, we've really designed Swift, we've taken Swift as a modern language. It's it's designed to do something better, to do something more modern also in the user interface toolkit. And that's what SwiftUI was aiming to be. So it came out in 2019. It was officially introduced with iOS 13. And kind of like Swift, it had also, a very furious start with lots of changes, rapid releases, and as usual, like, things cool down over time. But by now, 3 years later, we're now, Swift is a framework, right? So it's like a UI kit, it's a framework. So new releases of SwiftUI, sorry, not Swift, SwiftUI, come out with new releases of iOS, for example, right? So that's what's been happening in the past. So you might be seeing references to SwiftUI 1, 2, 3, 4, but really what that means is you need to add, let me see, 12 to that number to know that it's the SwiftUI that was released with iOS 13, 14, 15, and now 16. So now we are at a point where SwiftUI is in its fourth iteration, basically. And it actually is at a point where Apple is beginning to ship significant parts of its own system applications that it provides to you when you buy a Mac or an iOS device. It writes parts of these with SwiftUI. So, for example, if you have an iPhone, the Apple Pay flow, the new Apple Pay flow on iOS is built in SwiftUI in iOS 16. The new iOS weather app has been built with SwiftUI. macOS is the help viewer in macOS, not just iOS, has been written with it. And sometimes it's also just parts of applications that get replaced, like, for example, the activity stream in Notes. If you've seen that in the recent version of Notes as an activity stream, that is actually written in SwiftUI on both iOS, macOS, and iPadOS, so all three of these platforms. But in a way, while Swift and SwiftUI are really sort of, the married couple, that they really belong together and they're evolving in close collaboration, UIKit isn't going away anytime soon. For once, when you run SwiftUI, what's happening behind the scenes is that if you deploy on iOS, then oftentimes actually UIKit functionality is being used to actually create the things that you declared you wanted in a SwiftUI. So you wanted a text field or something in SwiftUI, it may actually end up being a UIKit component that's being rendered. So SwiftUI, however, is not yet another layer of abstraction that slows things down. It is actually surprisingly fast, as tests showed, in part because SwiftUI does a very aggressive folding and collapsing of the view hierarchy before things get rendered. So it throws away a lot of the unnecessary sort of double and triple rendering before it actually gets out to the screen. It flattens things a lot, and oftentimes it reaches down right down to the metal, in this case, actually metal, the API for really fast rendering, kind of comparable to DirectX on Windows, for example, instead of using higher levels like core animation. So SwiftUI is not at all slow. It's actually a fairly fast framework. So I'm going to do this a little different than what you will probably find in most other classes, at least what I was able to find in all the other classes and courses on the web and so on. It's not as easy to get your hands onto, to get used to SwiftUI because there isn't like the textbook by Apple, for example. But I'm going to take a slightly different approach. I want to share some big messages with you, and these are the things that I think a university course should be focusing on, and this is the kind of stuff that I want you to notice and to learn from being exposed to SwiftUI, however briefly. And so I collected my big messages that I think SwiftUI illuminates really nicely. The first big message is maybe a bit provocatively, object-oriented programming is dead, long live declarative programming. All right. Now, as you probably all know, before object-oriented programming was there, people were programming in like procedural style, right? Pure imperative code, like C, for example. Why do you think object-oriented won out? Why did it become the majority sort of adapted programming paradigm rather than sticking with imperative before? Yeah.
It's easier to think that way. So
It's easier to think that way. I would have said the exact opposite when I was sitting there as a student and people were like, hey, OO is this new cool thing you should really learn. So I was like, what? I was thinking imperatively. So I'm not quite buying that, at least not from personal experience. I do see, however, your point that you say, like in the real world, there are objects and they may interact with each other. So many business cases are nicely mapped onto objects, and even user interface components are nicely mapped onto objects. So yes, in part. But that wasn't the most crucial thing, I think. Yeah.
I think object-oriented programming forces you to think in abstract concepts and in hierarchies, and this is harder to model with like strictly procedural programming.
Yeah.
And I think if you want to build bigger systems, it's easier to have objects that like are classes or subclasses.
See, and that's the key point that you just said. He said, the bigger systems you're building. I mean, applications, like software that people were writing that was being released was just getting more and more complex, and exponentially so. Right? Compare like a piece of code from like I don't know the 60s with what people were writing a couple decades later. So the applications that needed to be built had to be just more and more complex. There were more and more abstraction layers being put on top of each other. The stuff we were trying to do was just more complex. So for all these more complex things, object orientation was just a necessary step, a necessary abstraction to make it so that you don't drown as a coder in all that complexity, right? So object orientation gives you, you're right, this like crucial step up in looking at things from a slightly higher viewpoint. Why did C still stick around? I mean, there's still people programming in C, though. I mean, in fact, if you go down to like the low-level rendering or media processing code in macOS 10, that's still C. Yeah.
Yeah, different languages for different purposes. For example, for like high performance, low latency jobs, you use C or something like that. And for UI, which is very complex and should be easy to work on, should be iterate, you do something like Swift.
Exactly. So especially when you want, like when you have restrained memory available or restrained computing power, right, in an embedded device, or as you say in like a low-level code that needs to run very fast, that doesn't need an enormous level of abstraction complexity, but it needs to be extremely tight, then you do end up using C. So it didn't go away. And I'm predicting the same is happening right now, and you're part of that change happening right now with the move from object-oriented programming to declarative programming. So object-oriented programming isn't going to go away. It's still going to stick around, right? If you need to model a moderately complex business logic with interacting classes like, I don't know, customers and orders and whatnot, yes, that's object-oriented. It is natural to think about it that way, right? So it will stick as an object-oriented paradigm. But what we're seeing in especially interactive applications with the user interfaces becoming more and more sort of involved and requiring more and more, complexity and elegance and functionality in the UI, we're seeing that declarative programming where you just say, I would like this to look that way, and I don't care how the code gets there. I just want it to be sort of reflecting that state of my model in MVC speak. That is sort of another step up in the abstraction level. So declarative programming has its advantages for certain kinds of complex problems, and it gives you another leg up, another step up to manage the new levels of complexity. This was becoming especially noticeable when people were writing, for example, big apps using UIKit or AppKit on the Mac, because you know how you've got the model view controller paradigm, right? So it's clear what goes into the model code, stuff that stores data. It's also clear what goes into the view code. It's the stuff that renders things, right? And people were like, pretty much everything else needs to go into the controller, right? The controller is this beautiful place that has access to everything, so you can get to your views, you can get to your model. And so it was basically getting overloaded with a lot of code. And that is something that you can fight by having good software development processes or good rules of what not to put into your view controllers. But there's a more fundamental problem, which is a view controller's job was basically to say continuously sort of talk to the model and talk to the view itself and make sure that they stay in sync, right? So you were basically building an initial user interface in the MVC paradigm with UIKit, for example, and then you were continuously, each time something happened on the model, your view controller had to make sure that it detected that right and that it would tell the view, oh, by the way, this thing has changed. So things drifting out of sync between your view and your model are a prime challenge in complex view controller code. Maybe not in the projects that you had to build so far for this class, for example, but once you get to more heavyweight projects, this becomes sort of a nightmare. The fact that people were overloading also the view controller with more and more stuff led to some people saying MVC doesn't actually stand for model view controller, it stands for massive view controller, right? Because people were putting everything into the view controller classes. And there's another challenge, which is because view controllers were not just becoming fairly heavyweight, so model and view code was usually very thin, and view controller was everything else, but also, since they were directly linked to the views, they were really hard to test. Trying to write a test code for a view controller means that you need to basically manually drive the UI, and that's a nightmare. It's not fun. It's much more fun to test a class or test a struct or whatever type that you've written some piece of code that doesn't actually depend on live UI input. So what you do instead in SwiftUI is basically that your model is the ground truth, as we know, right? It has everything in there. And your view is not something that you create at the beginning and then you actively drive it to update itself and you carefully change it here and there to reflect your model. No, each time you ask the view to tell you what the data looks like, it actually creates itself at that moment, checks the current values of the model is the ground truth, and the view always reflects the current state of the model. That's kind of like the mantra of SwiftUI and of declarative programming in this style in general, that the view is always a reflection of the current state of the model, period. So that sounds really nice, but that means that if you want to do that, you have to write a lot of code, right? Because you need to constantly basically have something in place that keeps your model in sync with your view. Otherwise, we haven't gained anything. And that's where MVVM comes in, which is a paradigm that I'll talk about probably tomorrow in a little more detail, which is sort of the corresponding variation of the MVC paradigm that actually makes that possible. MVVM stands for model, view, and view model. So there is a third component now. It's no longer the controller. The view model is a new piece in this sort of triangle of responsibilities and roles, and I'll talk about this a little bit more. In short, what it does is it's the part that makes sure that your model data and your view data always stay in sync. And so you don't need to store state or anything in your views. It's all based on what your model is currently saying. The next one is what you will see in SwiftUI is when you specify your user interface in code in SwiftUI, it actually almost looks like a web page. It almost looks like HTML code, to put it simply. Because what you will see is that thanks to things like trailing closure syntax and stuff like that, you will have like a hierarchical tree view almost laid out in code for you to see how your user interface fits together. And that means that modern languages that are generic, like the universal, like Swift, can be flexible enough to actually also work really well as what's known as domain-specific languages. Domain-specific languages are languages that are really designed just to do one thing really well. For example, specify a UI. And so modern languages like Swift can do that. Older languages weren't able to achieve the same level of syntax flexibility and have the same syntactic sugar to do this, but Swift does. And it's a good example of what modern languages are able to do. What you will also see, and this is probably going to be a bit of a surprise, that you will actually be able to design your user interface in code or in the graphical editor, and both are perfectly, basically, are accessing the same stuff. So you're working on one and the same representation of your UI, whether it is in code or whether it is in graphical editor. That is pretty unusual too. Right? If you think back to how you did it in UIKit, you were building your interface in Interface Builder, but there was no one-on-one representation of readable code that you would want to look at that would represent what you were just doing. Right? You wouldn't go in and just fiddle around with the code of the UI component that you have just dropped into Interface Builder. And so here, that's what we're going to be doing. We're going to see that the UI can be represented by both graphical and textual representation very cleanly, and can be, you can move back and forth at will, basically, and edit one or the other, and they both are one and the same thing. And finally, I think what you will see from SwiftUI is that if you really want a language to be high performance, and with high performance, I don't mean just that it has to run fast. I mean mostly it has to be fast to develop with, right? Because that's the big expense to pay people like you guys, who are going to make a ton of money as developers, maybe. So developer is expensive, right? So development time is expensive. And so a really good language to write applications with has to evolve today, has to evolve together with its IDE, and it has to evolve together with its user interface toolkit. Because apps, at least, are things that are incredibly user interface code heavy. And so the UI kit, or the user interface toolkit in general, and the IDE to build with it and the language have to evolve in close lockstep. And that's exactly what's going on with SwiftUI and Swift and Xcode right now. What we'll also see is SwiftUI isn't just letting you write declarative code and more easily write mobile apps, but actually this declarative, this stepping away from the how am I going to create this interface to rather saying I'm going to tell you the end result of what I want, is actually also making it easier to write code that you can deploy on the mobile device and on the desktop at the same time. And so overall, I think you may end up enjoying SwiftUI. Maybe you'll hate it. Maybe you'll never write code for Apple platforms again, and you'll move to I don't know, Android phones or Windows desktop. But whatever you do, I think what you're going to see is that if you look at SwiftUI from an observer's perspective, what's happening there these last essentially 3 years actually, it's a wonderful case study of seeing a major OS family, iOS, Mac OS, iPad OS, seeing that family moving through a paradigm shift in how code is being written for that platform, with all its growing pains and its problems, and how that happens and what it means for development is really interesting to see from this perspective. And there's a lot to learn from that, even if you don't end up coding in this particular environment in the future. All right, so I think in all, what we're going to do after this really high-level overview, I'm going to show you what it looks like to work with SwiftUI. So we're going to move to a quick coding demo that is really, really minimal. But I want you guys to see how it feels to work with SwiftUI. Oh, a quick poll here. Who has used SwiftUI before? You can be honest about it. It's OK. Yeah. OK, so 3, 4, 5 people. All right, not too many. Let's move out of this here. Let's launch Xcode. So I'm going to also start mirroring here, hopefully. And fingers crossed that our recording device enjoys this. So what we're going to do now is I'm just going to, you see the welcome to Xcode here. I'm just going to create a new Xcode project, right? So I'm clicking on this. And there's lots of options here. Multi-platform, look at that. But we're going to go just for an iOS app, just to keep it really simple. I always love seeing like the most basic, simple, no-frills app to really see the bare skeleton of how something works. So it's iOS, and we're just going to create an app. Hitting next here. I'm going to give it a name, right? OK, so let's say this is called iOS test, for example, right? OK. So I have as interface here. That's one of the things you need to do. I've selected SwiftUI, right? Not storyboards. Storyboards are no longer with us when you do SwiftUI. And the language is obviously Swift and not Objective-C. And we don't use any of these advanced things here, like including tests or using core data. Just keeping it simple. All right, so creating this now. And what we end up with is this window. And I've blown up the font to like, otherworldly proportions so you guys can see what's going on. Really briefly speaking, you already know Xcode, so this is easy to explain. What you get from a SwiftUI project is essentially two Swift files. One is this one here. That's the iOS test app.swift. That's basically the main file that launches my application. We're not going to mess with that a lot, right? But what it essentially does is it creates a content view. And content view.swift is the second file, and that is where our code goes. Right? So this is where you will be working when you start out working with your own interactive Swift application. So let's look at what this, the rest of this interface is doing. While this code is running here on the left-hand side, what you can see here is that we actually have a preview. And this is not the simulator running. So the simulator is this extra thing that boots up iOS completely and launches your app, your compiled, ready built app on a virtual device, right? So it's going to be 100% what you would get, hopefully, on a real device. But it also is fairly slow, and you can really only do this if you build the whole project. Now, what has happened in Xcode and the compilers behind the scenes and the whole runtime system is that it has been extended to allow you to basically switch out parts of your code while the application is running, which is kind of weird. It's almost like, replacing something inside an executable while it is executing. And because this is possible, Xcode can display what's known as a preview here on the right-hand side. And this preview is essentially showing me what my application will look like, but with one big difference. If I edit anything in my text field here, in my code, it'll actually change in the preview. So let me do that. I can go in here and change this hello world into hello Aachen. And you see immediately here on the right, this is updated to say hello Aachen, right? That should be a bit of a surprise, right? Because that's not usually what you get when you are actually coding an interface, right? And this is also a wonderful example of seeing how the same thing is editable graphically or in text. So here on the left-hand side, I've got a text widget. We'll talk about the code more in a second, but here's something that apparently creates this text. And I can edit it here in the source code, or I could go in here and basically stop the live preview and go into the view that lets me actually edit this stuff. So if I click on this guy, I can bring up an inspector on this thing, and it will tell me all kinds of things of what's in here. And I could also change the text over here, and that would basically reflect back to the code as well. Right? So it works both ways. I'm seeing the same kind of user interface components in both views. All right, so we have an inspector. We'll talk about this more later. We've got this preview, which is really nice. I've shown you that you can actually, when you move out of the live preview here, you can actually click on things and open up a couple things. For example, if I wanted to, I don't know, embed this thing in a larger view, I could do that here. I could see the inspector for this object. So I've got a lot of abilities to work with the graphical user interface right here in the visual preview of this file. Another thing that is kind of cool, let's see whether our space is enough for this, I can open up a variance view. Because maybe I want to see, this hello Aachen looks a bit tiny. I wonder what that looks like when people use dynamic text. iOS has dynamic text, right? You can set a dynamic slider in the system at one point, and all the apps that use dynamic text will adjust to the right size. So let me do that. Let me click on that. And all of a sudden, I'm getting a lot of previews here. And these previews are all using different text sizes. Let me make that a little bigger so you can see it better. Maybe also hide this controller, this inspector. And as you can see, this is extra small at the top here. And then it goes on all the way to extra large, triple extra large. And then come the assistive technology modes. If you can crank up your text size even further in assistant settings. And those go up all the way to this very presentation-friendly AX5 size here. Right? So that's what your different dynamic text sizes will look like. So this way you can verify that your user interface still looks okay. It doesn't wrap around in a bad way, but it's still readable also in any way. Other things you could do here is you could look at your light mode and your dark mode at the same time, just in two different views at the same time. So this is really nice and shows, hopefully, that Xcode and its live previews in this canvas here are a really nice way to get a very quick feedback on how your interface is looking. Couple things here. This live preview is fairly compute intensive, so it occasionally pauses itself when it feels like, oh, I'm burning through too much battery here, or the changes are too drastic to do the live recompile of parts of the code. Then you need to re-enable it by hitting that button here or pressing Command Option P. That will become a keyboard shortcut you will probably know by heart very soon, because every time the live preview pauses, you hit Command Option P and it restarts again. OK, let's go back to the slides again. I'm going to stop the sharing here in this way. All right. And you've seen this, right? So we've looked at the interface here. And I want to look at the code. And as I said, I want to look at the shortest possible app that we can think about. So let's see what we can learn from this code. I would like you to pay fairly close attention to the lines of code that we're going to talk about in the next couple minutes, because each line has one big part of how SwiftUI works that you need to understand. So what can we learn from this code? First of all, we're importing SwiftUI. Well, not too surprising, right? It's a framework. We import it. That's the one we use. What you should be paying attention to is that the only things in your project when you do SwiftUI that do import this should be views. A view is anything that puts stuff on the screen in SwiftUI. Anything that puts stuff on the screen in some way as part of the responsible for the user interface, rendering the user interface, is a view. Everything else is not. It should not be importing SwiftUI because, again, testability. You want your other classes to be testable without having to rely on the user interface code. Otherwise, automatic testing is a nightmare. Next up, we've got a struct. So as we learned before, Swift uses structs a lot. Structs are much more lightweight than classes, right? Classes come with much more baggage, more memory requirements, and they tend to be slower to manipulate. Structs are incredibly fast to create, to destroy. They are basically, no more expensive than an integer, right? That's how you can think about it. So our view, the content view, remember that was the one that was created by our launching app, right? That's the one that we were just seeing, is a struct. It's not a class. What did your views in UIKit look like? What were they? Structs? Classes? Yeah? Huh. Classes, yeah. You moved. That's it. That's right. All your UIKit views are classes, right? So they're fairly heavyweight. And that's OK, right? But SwiftUI takes a different approach. So your views are actually just structs, very lightweight data structures. And what else are we seeing here? Well, we're seeing that our content view is told that it needs to, what does that mean, :view? Yeah? It needs to implement a protocol. It needs to adhere to the view protocol, right? So let's see what it's going to do in order to adhere to that protocol, because it has to be in the code. Otherwise, the code wouldn't compile, right? View, by the way, is the basic protocol anything has to conform to if it wants to draw on the screen. You cannot draw on the screen if you're not part of the view protocol in SwiftUI. So here's what the struct does. It actually has a variable. The variable is called body. And that variable is of a kind of weird type. It's also fulfilling the view here in some way, but it's not a fixed view. It's not just saying colon view. It's something else. And this sum here is a particular modifier that SwiftUI needs in order for this to work. What this is saying is that the content view has a variable, the body variable, that when the code is compiled and is run, will actually return a view. That view may be a text view. It may be something else, an image view. But it will be something that adheres, again, to the view protocol. Why do we have to put some view there? Well, because body cannot decide on the fly whether it's going to return an image or a text. It needs to decide that at compile time. It is not dynamically exchangeable in terms of the type of view that gets returned. So let's look at how the body variable works. What kind of variable is this body here? It's a property, right? It's a property, but what kind of property is it? The curly braces give it away. Yeah? It's a trailing closure syntax that we're seeing, and so it's a computed property, right? It's a computed property. It's a property that I'm not giving it any value here per se. I'm saying whenever the struct content view is asked for the value of its body property, it will compute that property by executing this code. And that's exactly what I was explaining a minute ago, that in SwiftUI, all your views will always just reflect the current state of your model, right? They will be recreated on the fly the moment you ask for them. Right? They're not storing the stuff and then you need to send them updates to change their state so that they match your model. No. Every time you ask a view for, hey, what does this UI look like right now, it will compute it as a computed property. And that's exactly what this body variable is. So, by the way, so this is the only thing inside the view here, right? That's it. After that is just a closing brace. And we're done with our content view. Look at that. That's all we need to do to create this user interface that you just saw. Well, this is a simpler version, right? That has just one line of text in it, no globe image there. I just wanted to keep it really simple. You may, of course, add, and you will add more properties to your views over time if you add stuff to them. But this is the one that is required to fulfill the view protocol. OK, so what we also see here is that in the curly braces, we've got this text thing. So what is this, syntax-wise? What is this? Play Swift compiler for me. What are we looking at here? What would you call this from a programming point of view? Want to take a guess? Yeah? Well, either of you guys. You can make up your mind together. It is creating it. Yeah, it's an initializer, right? It's an initializer that is creating a struct of type text, right? So that's obviously the initializer for a struct of type text because it has the round parentheses around it, right? So, all right, so we now have created something of type text, and it gets a string to initialize itself. Maybe there's also one that doesn't take a string. We don't know, right? There could be several initializers, but this is an initializer, right? And text happens to be a struct that also conforms to the view protocol, right? So when this body variable computes its value, it's asked, hey, what are we looking like right now? It says, oh, right now we are a text field, or like a text view. Then it fulfills its requirements because it is returning a view, right? OK, and so what this initializer does is simply draw a static text on screen, right? That's exactly what this initializer text with the parentheses does. And that's it. That's all our code. Well, there was something else, right? There was some more code beneath that. So let's look at that real quick. It's this stuff here. I don't want to go into too much detail here yet. We're going to cover it later. But what this is basically doing is it defines how your preview looks. So you don't get this nice live preview thing for free completely. There's a little bit you need to do. Although this stuff is auto-generated, right? If you don't need to change anything about this, this gets auto-generated. You don't need to type any of that. But what it does is basically it says, well, if this thing is asked to render itself in the preview, it's not a full app, right? It's just a part. It's just, you could think of it as a screen in your app, basically. So it needs to know what it's supposed to display when it's being called all by itself. In our case, it's exactly the same. So our preview says, just return a content view. Just return the exact same thing that the app itself does when it launches. Remember in the launch, in the main application, we saw it basically just instantiates a content view. So here, the preview looks exactly like the real thing. There's nothing going on. But there are cases when, for example, you are writing, let's say, an app that lets you make a number of reminders, right? And then each reminder you can go into a detail screen. And now you're designing that detail screen. Okay? Let's say you've got this screen as a detail screen. Well, in the real app, the app will create the detail screen with the detail that's in the database, right? So the detail screen itself won't have a detailed content yet because it gets it from its environment, from the list or something else. So for testing purposes, you then need to provide some dummy content that you can render if somebody just wants to see the detail screen without running the whole app. Right? That's why this sometimes becomes important. You may need to do something down here. All right, so that's the shortest SwiftUI app. Isn't this elegant? Right? It's just, basically, I have to create a view, and it has a body variable. It's a computed property, and that needs to basically return some view, and I'm done. So with all of that, you might say, well, this is great, but I saw more than one thing in the demo app already on the screen, right? There was a globe and a text, so how does that work? Well, composing views is fairly easy. But there's one limitation. The body property that we just talked about can only return one view. So if you need to return more than one view, you can't just return two. It doesn't work, right? The computed property means it returns one thing, right? Just like a function returns one data type, the computed property returns one view. So if you want to return more than one view, you need to take all these views and put them into something else that is then a container or a layout view. And one example of these is the VStack. VStack for vertical, so it stacks things beneath each other. So what we're seeing here is an example of stacking two things above each other, right? So you see here, this code, I've left out the preview code because the preview code doesn't change at all. It stays the same for this. But the content view is now, the view that is returned by the body variable, by the computed property here, is now a VStack. And that VStack is created with trailing closure syntax. The trailing closure syntax means that the last parameter here, and the only parameter in this case, is actually a piece of code, right? It's a closure. And that closure actually, since it's now code, we can now write two things beneath each other. We can first create an image, then create a text, and this is two things. And this code gets passed as a closure to VStack, which takes these two objects here, these two views, and puts them beneath each other on the screen. And this is where your brain may start to hurt just slightly, because what we're doing here begins to look like, the parentheses that you might be used to, or the hierarchical nesting of, functions or if-else statements, something like this. But what we're really nesting here is basically inside the VStack we have two other views. And if you just for a moment imagine these curly braces to not be curly braces that suggest code but something else, it actually is, it almost looks like JSON, right? Or HTML code or something like that, or a document tree, like a document object model, a DOM tree. So that's what I want to point out, right? This makes the code almost look like a hierarchical user interface layout. Because I'm now, just by looking at this code, I can see, okay, my user interface is a vertical stack of two things, and these two things are an image and a text. And of course, you can imagine this goes on, right? You could, basically, this first one could have been an H stack, a horizontal stack of things, and that could have contained two things in itself. and it would all have worked out just fine. Right? So we're laying out our user interface basically by writing these nested trailing closure syntax things. And if you try to actually unwrap this, understand which code is being passed where, it hurts a little, right? But that's okay, because it makes for this wonderfully readable specification. So in a way here, modern universal languages, I said this at the beginning, right? So this might hopefully approve. Modern universal languages like Swift can actually describe a UI, like here in SwiftUI, almost looking like a domain-specific language. So that's an important point that I wanted to get across. VStack, by the way, is limited to up to 10 children. You might say, well, that's weird. Why? Well, because remember, VStack is actually taking arguments here, right? This is just a trailing closure syntax that says, take all these things and put them as children into this view. And this is being literally coded out for 1, 2, 3, 4, 5, up to 10 children. And then the Apple engineers got bored, or it was lunch break. They said, no, we're not going to do any more than that, right? If you don't want to do more than 10 children, there's ways around that. You can basically insert a group, which is an invisible container that takes its children and just passes them on. And then you get out of that trap that you can't have more than 10 arguments being passed here into this trailing closure syntax. All right. So now you might say, well, this is great, but can we modify this image or this text? What if I wanted to make this text a different color or larger or anything like that? Well, this works with modifiers. So modifiers are basically used to adjust views. And again, the way it works is different from what you're used to. Because a modifier is actually, you can see this from the dot syntax, is actually a method of the view. Right? So the view here, the text view, has a method called padding. And when you call that, you don't pass anything in there. What it does is the method actually returns a new view. And again, this is SwiftUI. So we are not modifying the existing label struct. No, we're just tossing it out, throwing it away because it's a struct, it's super cheap, and we recreate a new one that has the padding in it, and we return that instead. Yeah, and everybody who's like used to classes and objects and stuff is like, ooh, that's a lot of overhead, right? But it's not, because structs are really, really cheap. They're like I said, like integers in terms of the computational effort to create and recreate and destroy them. So what this is doing is that the text initializer here would first return a view that contains the string label. Then it would, this modifier, this first modifier would execute. It would throw away the old one and return instead a new one, which has the padding around it. Then the next modifier, this is a view again, right? So the view can have another modifier, which is this dot background. It's a method being called on the returned view from padding. And that one basically then just sets the color to red, throws away the padded one, replaces it with the one that is both padded and has the red color set. And that is a view, so you can call a method on it, which is a modifier, which takes the one with the padding and the red color, throws it away, and creates a new one instead that has a corner radius of 60 now, instead of the default that is, no corner radius, like pointy edges. So this is important to understand. Why? Because order matters, right? As you just saw, this gets executed first to last, right? So if I switch this around, things are going to look different. Also, I think I have an example for that here. So if I did it this way, I first applied a corner radius of 16, and then did the background color red, and then did the padding, I would get a different result out of this. You can play around with this yourself. This is sometimes a little tricky to understand why exactly this is going on this way, and it's something you can trip over quite easily. But if you apply these things to containers, so if I apply, for example, this kind of code to a VStack, for example, the background color, it will actually apply it to all its children. So it trickles down the view hierarchy that you have built up maybe in your UI code. What kind of modifiers will you be coming across? Well, you might be seeing font a lot, although not the way that you probably think, because you're not going to see things like font Helvetica 18 point or anything like that. No, again, SwiftUI provides you with abstract font notations, like abstract font types, like a typical font to use in a title, or a typical font to use as a level 2 header in your user interface, stuff like this. And they have these names, right? They are called like large title, for example. That's probably the biggest one you can create. And that's necessary because on iOS and on macOS and iPadOS and maybe even on your watch, it's all going to look different, of course. It's going to be a different actual font size. So we're using these logical names instead that are predefined. And there's a nice short way to write this. You don't actually often need to put font, like, dot large title behind this type. You can just say dot large title. Right? That's enough. You can leave out the type in front of that. Another one that you'll often see is foreground color, like dot foreground color is a typical modifier that you'll often see with views. It's not dot background color. That actually doesn't exist. This is dot background, which actually adds a whole layer behind the view. So it could be a color, it could be a material, a hierarchical shape style. So backgrounds actually need to conform to a particular protocol to be usable as background modifiers. Another one that you may often see is dot frame, which takes the view and puts it inside an invisible frame around it that has the specified size constraints. So that's a way to put something into a larger, frame and position it on screen. If you want something to extend to the device edges, this is why you could do this. You could just say, for example, dot frame with maximum width of dot infinity, which means it's going to be as wide as it possibly can to get to the edges. And finally, we've already seen dot padding, which just adds a little bit of space around the view on all sides. All right, now, so this is how you can modify views, right? You use modifiers, and every view type, every type that conforms to the view protocol, I'm still almost tempted to say subclass, but it's not a subclass. It's protocol-oriented programming is what we're doing, not object-oriented programming in this case. So every view type will have specific modifiers that only work with that type, that only make sense with that type, and you need to look them up in the documentation. Now, a couple more words about this preview thing that I showed you. So you've seen that your preview in Xcode lets you actually see your layout in the canvas. It's called the canvas, the stuff to the right here of the editor, without actually launching the external simulator. You can still do that. You can still run your thing in the simulator. And sometimes to really, really see how it all plays out and plays together, especially to navigate between different views and all that, you may need to run the simulator. But a lot of stuff can be done in the canvas. The big beauty, of course, of the big advantage is that it changes instantly while you edit your code, and it can be used to provide dummy data to your test layout. I explained that already. And you can also, as I showed in the in the demo, show dynamic text sizes or maybe switch to, for example, dark mode to see things differently and see how your interface plays out on different device classes. What does it look like on an iPhone 12 versus an iPhone 14? That's kind of similar to what you know from UIKit already, I think. So here's an example of a content view that you can see here that creates a body that returns a VStack that has a text in it and has an image in it and puts some padding around all of this. And the text is being modified with a whole bunch of different changes, right? It says, please use a large title for the font, use the orange color, put some padding around it of the following size at the top and the bottom and on the leading edge. And the trailing should be a little different. Leading and trailing is the left and right, or right and left, depending on your writing system. And make that text bold too. Right? And then we have an image here that's being inserted, and its color and scale is being adjusted. Now what you notice here is that actually this VStack can't just create itself from scratch. Initially, this text here is empty, right? It would basically return with an empty text. Now, But that could be okay if people were to create this, if in your actual code, this text got filled in somehow by a parameter when this view is being generated from somewhere else, right? But right now, here in this sample case, we don't have that somewhere else to run. We only have this available, and this is the only thing we can preview at the moment. So that's why, in this case, the content view preview down here actually doesn't just call the content view by default, but it actually fills in some sample dummy data, like hello iOS, so that my content view has something to work with, right? Because it's not running as part of a full app. Okay, a couple options that you might see or might use. You can choose a preferred color scheme, like dark mode, for example. You can set that to have your preview always come up that way. You can say which preview device you want to use. This is all just for the preview part down there in that code that I said that we're not touching very often. But if you do want to go in, you can do that. You can choose a different environment. You could actually duplicate that code at the bottom and just have several of these, and then you would get different kinds of previews side by side with different settings. You can change a whole bunch of things in the preview to make it look the way that you want it to, or the way, if you want to understand, does this still work on dark settings, for example. And then finally, the attribute inspector is a powerful tool that I've shown you. This was the one that was on your right-hand side of the editor, just like with UIKit, where you can change various modifiers, and other properties. So when you have something like dot padding, this also becomes something you can edit in the attribute inspector. You don't have to write this in code. But if you do change it in the attribute inspector, it plays right back into your code, right? So the code that you see, the textual code, and what's in the attribute inspector is basically the same thing. It even is smart enough to adapt the code. So if you, for example, set top and bottom padding in your attribute inspector, it will collapse these two to say dot vertical, because that basically means top and bottom is both on. And so it will sort of simplify your source code in a certain way, in this way. So what I'm hoping you can see from this is that, yes, you can design a UI graphically and in code at the same time. And I think it also becomes clear that SwiftUI is a format that really has to, shows that the language, the user interface toolkit, and the IDE, if they really evolve together in a close lockstep, then you end up with the most sort of productive interfaces and environments. All right, we are now at layout views, folks, but you need a half hour for going over the seminar topics as well, right? So what about we do a cut here, and tomorrow we're going to discuss a bit more about like what kind of ways there are to lay out things in SwiftUI, and also, of course, how to get user input back and write applications that actually consist of more than one view, right? Right now we haven't even moved between different screens in a simple app. Okay, well, with that, thank you very much, everybody, for today, and we'll see each other tomorrow again to continue and wrap up SwiftUI with the last class of the iOS course, and then we're going to move on to the seminars. Thanks.
This content was provided by RWTH Aachen University.